Hello, welcome to another video about circuit analysis. This one's about superposition as opposed to loop analysis or nodal analysis. Superposition is the idea that each voltage or current source can be replaced by its circuit equivalent without the voltage or current being there. So a voltage will be replaced by a short circuit and a current source will be replaced with an open circuit. And then by doing this for each separate source in the circuit, the voltage or current that's wanting to be found, such as Vn on this example, as was on the previous examples, can be found by adding together the voltage from each of these sources. So it's sort of looking at it as though there's a contribution from this one and a contribution from this one, making that voltage there. So this circuit can be redrawn like this, with one's short circuit instead of that V1, leaving only V2 and R2. Oops, must have missed that off. It's not a fuse. And it can also be redrawn with V1, R1, R3, R2, no V2, and these two voltages will be Vn1, Vn2, and if you sum Vn1 plus Vn2 should equal Vn from up here. So to work out Vn, it looks a little odd like this, but if you imagine R2, and in this case next to R3, you can see that those are in parallel and they're in series with R1, and we're looking at the voltage across this parallel pair. So this looks like a potential divider, just with two resistors down here in parallel. So that can be written out. That's V1. So Vn2 equals, using the potential divider equation, V1 times the resistance with the voltage across that you're measuring. So that'd be these two in parallel. So R2 times R3, R2 plus R3, over the sum of the resistances, R1 and the other resistance, which is parallel. So that will be R1 plus R2 times R3, R2 plus R3, and Vn1 equals, similar way, this is the same but flipped with different numbers, R1, R3 and R2. These are in parallel, that's in series, voltage across here, potential divider equation. So it's V2 times those two in parallel, R2, those two in parallel, R1 not R2, times R3 over R1 plus R3, 1 over R2, that's the one in series, 2 plus R1 times R3 over R1 plus R3, and putting those into this equation, V1 R2 times R3 over R2 plus R3 over R1 plus R2 times R3 over R2 plus R3 plus V2 R1 times R3 over R1 plus R3 over R2 plus R1 times R3 over R1 plus R3 equals Vn. So this, depending on, it's quite a simple, quite an easy way of finding out the voltages Vn voltage Vn or any of the currents. It works in a similar way. Add the contribution to from each source up to find the voltage or current at that node. With a lot of sources, it might take much longer. It will take a much longer time because you've got to account for each one of them separately and add them up at the end. And with these potential dividers, with more complicated circuits, you might end up with a series and then a parallel and a series and a parallel, and these equations will get bigger and bigger. But if you're doing this with numbers, you wouldn't have to write out the equations like this. Obviously, this is a lot more verbose and a lot larger than the equation we got from nodal analysis, for example, but it would simplify down to the same thing. But with numbers, instead of these names R2 or 3, it can be cancelled out, simplified, or just put straight into a calculator. So this isn't really a useful way of getting a universal result, but it is quite a nice way of getting an answer, and you know it's going to work. It just might take a bit more writing, typing out in a calculator. Yeah, if there was a current source, it would say, if instead of V2 there was a current source, there would be nothing here. We could have ignored R2, and then of course when we're leaving the current source there and getting rid of the voltage source, that would be a short, like it was in these two. Okay, thank you. That was a quick demonstration of superposition, and yeah, thank you for watching.